All right, now to covalent honors stuff. Okay, so we want to fill in pairs, and I think I left this whole sentence off for you here. A few more trends I want to go over between the difference between ionic and covalent, but today we're focusing on the idea that electrons are shared for covalent. And, you know, for the honors extra material that I'm going to want you to do is I'm going to actually want you to draw sort of a little diagram indicating how electrons will be shared. And we won't do dots, we're going to do line diagrams. So you'll see how that works. But one thing about covalent bonds is that electrons are always shared in pairs. When we did ionic bonding, we'd often have one valence electron goes over here, one goes over here. But no, in covalent, everything happens in pairs. Electron pairs not involved in bonding are called either unshared, lone pairs, or unbonding pairs. And we have 4 types of bonds, a quadruple bond being kind of rare, but single bond, double bond, triple bond, quadruple bond, depending on how many pairs of electrons are shared. And why do you think we even stop at 4 anyway? Because we wouldn't go past that. Why? Because you'd have more than 8. And 8 was sort of our magic stable number. So as long as we can be, so that everything's got 8 or 4 pairs, then we're happy. All right, so I'm going to want you to draw some structural formulas for me. We've done some chemical formulas for ionic bonding. So if I give you a chemical formula, can you draw me the structural formula?
Yes.
Well, you will. So the structural formula shows how atoms actually bond. You could do it with dots, you could do it as a full bore model, or you can do it as line diagrams. Again, we're going to focus on the line diagrams. And this is a correct diagram for water. Being a little careful to realize that H, hydrogen, isn't a metal. So this is a covalent bond. We've talked about that. Even though hydrogen is on the left-hand side, these are all nonmetals. So this is a covalent bond. And this is what a line diagram would look like. Okay, so how do we know how to draw that? Well, not yet. Okay, we'll go through the rules on the next slide, but valence electrons again. How many electrons do you have to work with anyway? Here's an example of chlorine. Chlorine's got 7 of its own. So a structural formula would show 1 bonding pair, which we always draw like straight between this. It's connecting them. Because that's our bonding pair. The rest are sort of like going around the box again. Exactly. So the next one is a double bond. We do try to make it symmetrical as possible. So that means oxygen's got some lone pairs each. So those would be line diagrams for these examples. Then even a triple bond, 3 lines connecting.
Is there a little twist?
No, the twist is, how did I know oxygen would have a double bond? How did I know how many lines to draw? Okay. What if I don't give you the dot diagram?
Well, what if then I got the 2?
Then you go to do that.
Good. It is all about figuring out how many dots you got. All right, we good with this?
Yeah. Oh, you just look at the electrons, man.
All right, good. You guys getting it? Okay. So if I give you a chemical formula without a structural formula with the dots, and I ask you to draw me a line diagram, this is how you do it. You're all correct. You want to know something about the dots. You have to add up the total number of valence electrons you have, which that's easy. Then, since everything happens in pairs, divide by 2. I don't care about total valence electrons, I care about how many pairs of valence electrons. Whatever that answer is, that's how many lines you have to draw. You can't draw more, you can't draw less, because the lines represent how many valence electrons you have. You have a set number of valence electrons. All right.
It won't be more than 4?
Good. But we won't have more than 4 lines touching any one element.
So we won't have more than 4 lines in between the two.
Right. And we never have more than 4 in between either.
I have a question. If you go back one slide to the end two, how come you couldn't just put a pair like below them and then have one pair out to make it a single? Why does it have to be a triple?
Ah, okay. Good question.
Yeah.
Why is this a triple bond? Because, again, it comes back to the number of dots you have to work with and our magic number of 8 dots or 4 lines. But see, these 6 electrons here sometimes are going around this nitrogen. So together, each sort of has a set of 8. And that's, again, still the point, the octet rule. Do we have 8 valence electrons around each element? So same here with oxygen. It's got some of its own, but then we're sharing 2 pairs. So these 2 pairs are sometimes going around this oxygen, sometimes going around this oxygen, but together they each sort of have a set of 8.
So like if you did do that, I would only have 6.
Right, so that's why it would have to be a triple bond. Okay, so good. Back to the idea of 8 valence electrons is what we desire. But since we're not doing dots, we're doing lines, that would mean 4 lines. Except for hydrogen, which is so small, it's only going to want 1 line touching it, because hydrogen's still in that very first energy level. And how many electrons can fit in that very first energy level? Just 2. So hydrogen only wants 1 line touching it, and then we're going to try to make them as symmetrical as possible. So here we go. So here is a chemical formula, SiO2, which you recognize as being covalent. Why?
Because they are banged together.
There's no metal. Shh. Another good point.
Okay, Si and O.
Okay, Si and O are on the right-hand side. They are not metals. And now we will introduce column 14 a little bit. We kind of been ignoring that in ionic. We first have to figure out how many electrons we have to work with. So Eric, you've got 1 silicon here. How many valence electrons in silicon? 4. All right, and then we have oxygen. Noah, how many valence electrons does oxygen have? 6. Noah, how many oxygens are in the formula? 2. So you've got to add in 6 twice. Does that make sense? You have 2 oxygens. They each have 6 valence electrons. We get 16. So that's 16 dots, 16 valence electrons. But, Sahil, how many pairs of electrons would that be? Okay, so I apologize. The audio went bad, and I'll just do a little voiceover for the rest of these slides of notes. So as we were saying, silicon and oxygen here would have 16 total valence electrons. But we no longer care about electrons and dots. We want to draw lines. So divide by 2 will give you 8 lines, because again, a line represents a pair of electrons or a pair of dots. Then we would start to draw it, and we want to set it up somewhat symmetrically. So we're going to have the silicon in the middle, surrounded by the 2 oxygens. That would be our most symmetrical setup. And as you can see so far, I've added 2 lines to this picture. We know we have to draw 8, but this at least would be true. There's definitely going to be a bond between oxygen and silicon. Maybe it's a single bond, maybe it's double, maybe it's triple, but it is at least a single bond. So since we have 8 lines to draw, we'll just kind of do a guess and check for the rest of this. We'll add our extra lines around oxygen. We're making it somewhat symmetrical, so that's nice. They won't always be perfectly symmetrical, but as symmetrical as possible. So we've got 1, 2, 3, 4, 5, 6, 7, 8. So we've added all the lines that we're supposed to add, but now we've got to check our very last rule. And our last rule says that there needs to be 4 lines touching each atom. So this oxygen is great. It's got 1, 2, 3, and this bonding pair counts as well. 4 lines touching it. Same with the oxygen on the other side, 1, 2, 3, 4 lines touching it, so it's happy. But this silicon in the middle is not stable yet. It only has 2 lines touching it, and it needs to have 4 because, again, lines are pairs of electrons, and that would be our magic number of 8 valence electrons. So when it seems like something is unstable and you've already drawn the lines you're supposed to draw, you have to rearrange them and you have to think of higher order paired bonds. So not a single bond anymore, but we're going to have to move one of these lines and make it a double bond. So we'll do that for this oxygen, and of course we'll do it for the one on the other side. And that way we didn't add any extra lines, we still have our 8 lines, and this silicon in the middle is now happy because there are 4 lines touching it. If you look at it surrounded, it has 1, 2, 3, 4. This oxygen also has 4 because those bonding pairs count for it as well. Likewise for this one on the right. So that is the correct structural formula up here. All right, now let's try water. We'll do the same first steps that we did for silicon and oxygen up here. We start by adding up all the valence electrons. Hydrogen is in column 1, so it of course has 1 valence electron, but there are 2 of them, so add in that 1 twice. Oxygen is in column 16, so it has 6 valence electrons. Add it all up, we get 8, but that's 8 valence electrons, or 8 dots. I really want to divide that by 2 to learn that there are 4 lines I need to draw. So I have to draw 4 lines, no more, no less. Set it up somewhat symmetrically. We'll have oxygen in the middle, hydrogen surrounding it on the sides. I know this is at least true, so we've drawn 2 of the 4 lines I need to draw already, and then I'll just come back and add the extra 2 lines. Now, where do I put them? Well, in this case, I'm surrounding them around the oxygen because hydrogen was an exception. Remember that hydrogen does not want 4 lines touching it. Hydrogen is so small that it can only handle 1 line touching it, or 2 valence electrons. So these hydrogens were already all set, but we needed to make oxygen stable by adding a line on the top and bottom. So this is water, and this is a covalent bond. These are being shared, these 2 right here, or these 2 sets right here. Don't be thrown off because hydrogen's in column 1. Remember, that is an exception. It's not a metal, it is a gas. So these are non-metals, so this is a covalent bond. Just don't forget hydrogens only want 1 line touching. Alright, now we'll move on to naming the binary compounds. Binary, of course, meaning there are only 2 elements. There are different rules for some bigger covalent compounds, but we're going to stick with binary for the moment. We will still add "-ide" to the end of the last element. And then we're going to use a little prefix chart on the next slide to indicate how many of each element I have. Another couple rules: mono is never used for the first element, kind of a weird rule, and then we don't have double vowels, so drop an A and an O if needed so you don't have a double vowel. Alright, so here is the prefix chart. Some of these are probably familiar to you, some of them may be a little new, but 1, mono, 2, di, 3, tri, tricycle, 4, tetra. I like to think of the game Tetris. All the pieces in Tetris are made of 4 little blocks. 5, penta, like a pentagon. 6, hexa, like a hexagon. 7, hepta. 8, octa. 9, nona. And 10, deca, like a decade. It would be 10 years. Alright, so here's a couple examples. If I wanted to name this covalent compound P4O6, well, now I need to indicate the numbers of each atom that I have. So to say that I have 4 P's, or 4 phosphoruses, just look at your chart. 4 is tetra. So you'd say tetraphosphorus. And then look at the chart for 6. 6 is hexa. And then you have oxygen. But we're not going to have the double vowel. We don't want to say hexa oxide. We want to say hexoxide. So get rid of the double vowel. And of course make sure the end is IDE. So once more, tetra was for the 4. Hexa, although we dropped the A, hexa was for the 6. P is phosphorus. And then O is oxygen, but we still changed the N to ide. So tetraphosphorus. phosphorus hexoxide. All right, and now C and O. And here's a good reason or good example as to why we need these prefixes. We didn't need them in ionic bonding because there was only one way the metal would bond with a non-metal. But there are multiple ways here that carbon and oxygen would bond. You know the example CO2. CO2, well, we exhale carbon dioxide. Well, if I want to indicate there's a bond between carbons and oxygens, it's not automatically going to be CO, it's not automatically going to be CO2. I have to tell somebody with these prefixes what exactly it is. So C is of course carbon. One of them you would think would be mono, but we don't put mono for the first element. Weird rule, but leave mono off for the first thing, but you will use mono for the second element. So this will be not monoxide, but monoxide. So that is that deadly gas that can be found in your house, carbon monoxide. Again, no double vowel, don't have two O's here. And last example, water. What is the fancy chemical name for water? Well, 2 is di, H is hydrogen, and then one oxygen again would just be like up here, monoxide. So the fancy chemical name for water is dihydrogen monoxide. So next time you want to ask one of your teachers if you can get a drink of water, just ask them if you can go get some dihydrogen monoxide. All right, I did randomly skip this slide, so might as well go back over it, even though I know you know how to do it. Formula mass, what we just talked about, you add up all the masses of the atoms in a given compound. So H2O, multiply the mass of each element by its subscript. So what's the answer going to be for the formula mass of water?
2 plus 15 is 7, or 16, which is 18.
Hydrogen's mass is 1, but there's 2 of them. And do, round right away. I know you wouldn't necessarily do that in math, but round right away so we can all be on the same page. Oxygen's mass is 16, there's 1 there, 18. And that would be atomic mass units, or it could be in grams if we wanted to say it was a mole of water.